I'm going to talk about cold climate construction, and I'm talking about sustainable construction, and about the Alpine Club of Canada's newest hut, just built last year. In fact, finished up this winter, opened in March, which has cold climate and sustainable construction features. So this is a map of North America. So I come from a spot right about there, a little town in the mountains called Canmore, Alberta, Canada. It's about an hour's drive west of Calgary and about 2 minutes from the Banff Park gates and about 20 minutes from Banff. It says I'm in a very cold zone and I get 9,000 heating degree days, but actually we get about 7,000 because we're fortunate enough to get Chinook winds that come in the wintertime and warm things up. So one day it might be minus 25 and the next day it's plus 15. Something like your nor'westerlies, is that what you call it? Yeah, something like that. We call it a Chinook arch, and the warm wind comes in. So actually we're at about 7,000 heating degree days. And a heating degree day is just one way to define a cold climate. It's a function of how many days that are below 18 degrees Celsius, which is sort of the cutoff when you might want to think about putting heat in your buildings. So the number of days below 18 degrees Celsius times the number of degrees below 18 degrees Celsius. So for instance, yesterday morning when I was driving over from the Unwin Lodge, my car said it was minus 12. So that's 30 degrees below 18 degrees Celsius. And if it was minus 12 consistently for 10 days, that would be 30 times 10 or 300 heating degree days. So that adds up pretty quick. But what's interesting is that climate is affected by altitude as well as latitude. So cold climate construction applies not only to the polar regions, but also to the alpine. So as I talk about cold climate construction, I'm going to focus on three things. First, cold temperatures and what that really means for designing and constructing buildings. And then two of the most important design strategies for cold climates, which are heat loss control and moisture control. So first of all, just temperature in general, what does that mean for the design and construction of buildings? It means that our precipitation comes in the frozen form. It means extreme temperature shifts, like the Chinooks that I just described, from one day to the next. It could be a 30, 40 degree temperature shift. And also throughout the seasons. So the winter, minus 40, summer, plus 30. Wind can be very strong. We have something called DRWP, which is driving rain wind pressure, which you have to design for. We have freeze-thaw cycles, UV radiation, and maintenance. Maintenance can be difficult in a cold climate because you don't want to send your maintenance guys up on the roof when it's minus 30. And especially if it's a remote area too, it might take a while to get the parts in. So how do we respond to that? Well, we use robust building materials and mechanical systems. So materials that don't crack in cold temperatures. And we use sealants that will expand and contract with extreme temperature shifts. We design roofs that are able to take the snow load, so there are actually snow load tables that we use. Strong buildings, structural strength is important. Special design for building envelopes, and which I'm going to get into in a minute, concerning heat loss and moisture control. And we build backup and redundancy into the systems so that if something breaks down, we can actually make do until repair can occur. So just a word about spindrift and snowdrift. The definition of spindrift to a mountain climber might be loose powdery snow incapable of holding protection. But to an engineer or an architect, it's fine wind-borne snow capable of entering a building through any opening in the building envelope. So we have to design special vent covers for all the vents. And over here on the right is a guy digging out some propane tanks because they've been covered over by snowdrift. This is the Alpine Club of Canada's Abbott Pass hut. It's the second highest structure in Canada, the first being the Neil Colgan hut, which is also an Alpine Club hut. The Abbott Pass is located on the Continental Divide, so over to the left is Alberta and Lake Louise, and over to the right is the province of British Columbia and Lake O'Hara. So this is actually, so the hut is here. This is actually the toilet. So that's the throne room there, and this is where we store the barrels. So it's a barrel flyout system. And when the barrels need to be changed, there's a flight deck here. We just bring the barrels out, slide them out here, and they're flown out. But what I wanted to say about this one is that once, a few years ago, the door to the throne room here was left open only a crack, like a quarter of an inch or something. And it filled up completely with spindrift, and it had to be shoveled out before anybody could use the toilet. So one of the first two cold climate construction strategies is heat loss control. And heat loss happens through the building envelope, through the thermal envelopes, so how much insulation you have in there is a factor. And also you need to control air leakage, so I'm going to talk about both those things. Heat loss mechanisms are conduction, convection, radiation, where conduction is actually the most important one. So back in 1965, when my dad built our house, the building code stipulated 2x4 exterior walls, which is really 3.5 inches of insulation. And when I started studying architecture back in 1980, the building code stipulated 2x6 exterior wall. So that's actually 5.5 inches of insulation. Both of these examples, if this is inside and this is outside, this stud here acts like a thermal bridge and it conducts heat out. So that's why we came up with this alternate solution, still a 2x6 plate, but 2x4s are staggered so that we can have some insulation there, and which acts as a thermal break. Nowadays, starting in the 1990s and still now, this is our standard exterior wall. So it has an extra 2 inches of rigid insulation on the outside, and that acts as a thermal break here. And you just compare that to the passive house system, which is about 16 inches worth of insulation, which might seem excessive, but besides conduction, the passive house system, because it's so thick, it also stops heat loss through convection. So that's the magic in passive house. So I don't know how many people are familiar with passive house, but the theory behind passive house is that it's so well insulated and so airtight that you don't need a furnace. Okay? So the sun heats it up, people's bodies heat it up, cooking activities, electronics, and there have been thousands of houses built in Europe, Germany and Scandinavia, according to passive house standard. So a typical exterior wall in Canada would have 2 layers of insulation. And even the foundation, so we have basements, a lot of us have basements, and the insulation that's on the wall here, there's the first layer and the second layer. This one is actually carried all the way down to insulate the foundation wall. And what this does is it keeps this surface here, so the inside surface of the concrete foundation wall, it keeps that surface warmer. And so there's less risk of condensation there. And also you can see there's insulation under the slab. So this is a thermographic image of a wall. The blue or the darker colors are cold, and the lighter colors are warmer. This is a heat source, so it's probably a floor, in-floor air blowing up, warm air blowing up over the wall. This image, you can see vertical lines. It's just when you're looking at it with the visual eye, all you see is just the drywall. But this image shows you that in behind the drywall are the studs. You can see the studs going up and down, and those are actually colder than the insulation that's in between. And this image also showed me that there was some insulation missing in this wall. And so so air flows from hot to cold. Okay, that's just a building science principle. And I remember back when I was a kid, and if I just took too long to get in the house and close the door behind me in the wintertime, my mom would say, "Karen, close that door. Do you want a warm-up Maidstone?" And I thought that was kind of funny because I thought surely it's the cold air that's coming in. But no, she was right. It's actually the warm air that's going out. I don't know if you can see this one very clearly, but there's some vertical lines. Just barely see some vertical lines down here. This is just a regular drywalled wall in a bedroom. But what these lines are showing where the studs are behind it. And these lines are called dust marks. So the way that happens is there's warm, moist air inside, and it hits that wall. And just along where all the studs are, it's just a wee bit colder. And so the moisture tends to condense along those lines. And then the dust that's in the air naturally sticks to that, and when the moisture dries up, you're left with dust marks. So what do we do? Solutions for thermal bridging. So we used to put a lot of framework in corners. So now we don't do that anymore, so that's less thermal bridging there. And we add 2 layers of insulation. And then sometimes we can make it thicker and stagger the studs. So those are things we do to prevent thermal bridging. And the second way to control heat loss is to control air leakage. So another thermographic image here showing air leakage around the door and at the light switch and at the electrical outlet here. And the solution for air leakage is to install an air barrier. So the air barrier has to be impermeable to airflow, continuous over the entire building enclosure, able to withstand forces during and after construction, and durable over the lifespan of the building. And so in Canada, the air barrier is also the vapor barrier, and it's installed on the warm side of the insulation, and it must be continuous. So even when there's some kind of penetration here, like a light fixture, the air barrier still has to go around that. If we don't succeed, we could get something called ice damming, which the symptom of that is icicles forming. I mean, it looks kind of cool, but it's not a good thing because it can cause water damage in the attic. It can cause structural damage. Mold can grow, and then there might be health issues resulting from that. So the mechanism, how that happens is, so there's heat loss into the attic. And so we have a warmer area here, which melts the snow on the roof. And as that drains down the roof, it hits this colder area here near the eaves and starts to freeze again. Forms icicles, but this also forms a dam. So this water that's flowing down can't go anywhere, and it starts to back up onto the shingles, and then it starts to drip down into the attic. Solutions for ice damming is to make sure there's a continuous air barrier, to add more insulation in the attic, and that keeps the attic cold, because that's what you want. To provide ventilation, soffit vent, gable vent, roof vent, ridge vent. And in a pinch, you could put in this heat tape, which keeps that eave area warmer, so it keeps that water draining. And in Canada, we have something called a water shield. It's eave protection, and it's a building code requirement. So if there is any backup under the shingles, that there's a secondary shield there to make sure that water does not go into the attic. And finally, moisture control. So the overall moisture control strategy is in cold climates is to make sure that the moisture that's generated indoors does not enter the building envelope. And if it does, and some might, and probably will, to make sure that you've provided a means in which it can dry to the exterior. So we put an exterior sheathing on there that is vapor permeable. And just a word about condensation. Condensation can happen on windows, can happen on drywall and cause mold to grow, and can happen also on the interior surface of the exterior sheathing. So that means it gets through the vapor barrier and past the insulation and then finds a secondary condensing surface on the inside of the exterior sheathing. Strategies to control condensation is to increase the condensing surface temperature, provide a vapor barrier, ventilation, and of course source control. And to increase the condensing surface temperature, we usually put a heat source under windows. So that's why you'll find, some kind of forced air system that usually has a register right under the windows. So it keeps that window surface warmer. And we also use triple glazing. So for decades now we've had double glazing, but now the newer homes are going for triple glazing. And also this extra layer of insulation that we're putting on the exterior now, that keeps this surface warmer. So this is a secondary condensing surface, the inside surface of the exterior sheathing. We provide a vapor barrier on the inside of the warm side of the insulation, and it must be continuous. We provide ventilation. So, and in Canada, most of the newer homes and buildings are providing heat recovery ventilation. And what that is the warm air that's being exhausted is passed by the incoming fresh air, which is also very cold. They don't actually mix, but there's heat recovery from that outgoing exhaust air. And so that means your furnace doesn't have to work quite as hard. And it's an energy-saving feature. And of course, source control. So just controlling how much moisture is being produced indoors through cooking and showering and laundry. So by way of an example, this is the Alpine Club of Canada's Bow Hut, one of the 5 WAPTA huts now, built in the 1980s. This area on the right is the cooking facilities over here and tables for eating and relaxing, and there's a heat source in there. There's a wood stove. Over on the left is a sleeping area, and there's a corridor connecting the two, and there's a toilet off the back. And about 15 years ago, there was a problem with condensation on the sleeping quarters. And it looked something like that. And the maintenance guys had been going up every year and taking bleach and trying to clean that off. But mold has roots, and it just grows back again. So they brought me up there to take a look at that. And we opened up some of the panels, took a look inside the wall, and were relieved to find that the moisture had not penetrated the wall cavity. So the recommendation then was just to replace that plywood and to open up the space, because the sleeping area had been compartmentalized into 4 different rooms. So we opened it up so it had room to breathe a little bit. And we provided a heat source. So there was never a wood stove in that spot. So we require, to prevent condensation, 2 things: provide a heat source and provide ventilation. there's no energy source up there, so what we did is just popped in a little exhaust vent here, and it just relies on the principle that warm air rises. So some fresh air comes in to feed the wood stove. Warm air rises, takes the moisture with it, and out it goes. So not a very technical concept. It's actually called the Eskimo snow hole technique. But we had to put a special vent cap on that to prevent spin drift from entering. And another example, the old Lawrence grassy hut. That's a clue, the old Lawrence grassy hut. Up near Mount Clemenceau, which is the fourth highest mountain in the Canadian Rockies. There were reports of mold condensation on the inside of the walls. It's a Quonset style with corrugated steel cladding. And when we took a look at it, we opened up the wall cavity and we found that moisture had penetrated. And in fact, the structure, the wood laminated beams were soft. So Derek could actually just put a screwdriver into it and it sunk right in. So not structurally sound. The moisture could have got in because there were marmots that were also getting into this hut and destroyed the vapor barrier here. So the moisture producing inside the hut could have got past that vapor barrier and into the wall cavity. It could have been through wind-driven rain because of the style, the design. Or it could have been because sometimes this hut is just buried in snow. But for whatever reason, it was decommissioned. All right, so that's cold climate construction. And honestly, there are books written on this and courses that you can take. So 20 minutes is hardly does it justice. But moving on to sustainable construction. You can see sustainable construction requires increased efficiency. So in energy, water, building materials, you're looking at increasing your efficiency. It's about reducing impact on the environment and human health, and it's about doing that over the whole life cycle of the building through the design, build, maintenance, and demolition. And we're always striving towards sustainable construction. So there's nothing ever a perfect sustainable building, but we're picking and choosing which features that we can use that are appropriate for whatever you're doing there. You can also look at it as having people priorities, building priorities, and environmental priorities. Some of the features, just to give you a feel for sustainable construction, you might have some features that preserve the natural vegetation on the site, rainwater collection, reduce construction waste, using recycled, durable, local building materials, an efficient furnace, reduce heat loss through building envelope, renewable energy system, and some attention to indoor air quality. So probably the most sustainable building would be an igloo, right? So it is uses local building materials, zero transportation costs, recyclable building materials, durable materials, zero greenhouse gases to manufacture the building materials, zero environmental impact, easy to decommission, and affordable. But not very comfortable. It's it's a safe place, rather than just sleeping out in the outdoors, but not exactly comfortable. So back in 2009, I got a phone call from an architect out of Vancouver, and he'd been looking at the Bees website, and he liked what he saw. And he was interested in off-grid construction, and he asked if he could volunteer. And I said yes. And in fact, it was good timing because the Alpine Club of Canada and Parks Canada were just in negotiation about putting up another hut on the Wapta ice fields. How would we prevent condensation? Because all the other Wapta huts had some kind of condensation issue. What could we do differently? What would be the ideal design? So our design challenges included that it was off-grid, so that meant no power lines, no sewer, no potable water. It was remote, so we wanted to build redundancy into the system and make it easy to operate. Extreme low temperatures, extreme wind. Actually, we did a wind study up there for a year. We got heavy snowfall up there, drifting snow. Actually, that drifting snow that you saw earlier on, that was up at this site. Spin drift, moisture-producing activities, no live-in custodian, so very similar to what you have in New Zealand here, but not similar to what you have in Europe, where you have these big refuges? Well, yeah, that. Where there's actually somebody there to take care of the systems and monitor that. So we don't have that usually. Periodic use, so you have somebody in there and then nobody there for 5 days or 10 days, and then the hut cools down, and then somebody back again. So the thermal, there's a lot of thermal change in that hut, so it has to accommodate that. And national parks location, so this hut was actually built in the national parks, and they have certain restrictions on that. So we thought, well, maybe we could build a log hut. A lot of our huts are log, and I kind of like log because log breathes. So the moisture that's produced inside is absorbed by the log and expelled to the exterior, which works quite nice. It takes care of condensation, but it's not very energy efficient. Okay, it takes a long time to heat this up. Having said that, the second last hut that the Alpine Club of Canada built was a log structure. We could build in stone. So stone is a local building material. This is the Abbott Pass hut again. It was built around 1927, something like that. And really thick walls. And the wind really screams through here. It's a pass, right? But when you're inside, you don't hear a thing. It's thick, heavy walls, and you don't hear anything. So very structurally sound, but again, not very energy efficient. So this is the site just here, right here before any construction happened. This is the site starting the foundation. Construction started about the 3rd week in July last year. We had a biologist on site doing a biophysical survey, foundation work. And then we put on some solar panels, and there's one wind turbine, which feeds a battery bank, which runs LED lights and some ventilation fans. Electrical, $10,000 worth of batteries, propane burners in the kitchen. There's a propane stove for heating, supplementary heating. Drying rack above the propane stove, kitchen, and right here we have moisture control. So there's ventilation, there's exhaust. The moisture that's produced in the kitchen is actually vented out. Interior shot looking towards the kitchen. There's the stairs going up to the loft. And another shot looking the other direction. The upstairs loft with the sleeping arrangements. And there's also a ventilation up here to take moisture away. And we put in a drying room for wet gear. That's also ventilated, so that separates that moisture-producing activity from the rest of the hut. That's the work camp on a good day and a not-so-good day. And on this day, the cook tent actually blew away. So I think it was a particularly low morale day for the volunteers. But I think everybody agreed it was worth it in the end for this view. And the final product. So our vision was to build a structure that enhanced visitor experience and acts as a model for other off-grid facilities. So it's kind of a lofty vision. We had design goals, environmental integrity, advanced construction methods, reliability, reliable and easy to operate technologies, energy efficient, and of course healthy indoor environment. And you can put it all together in this nice little graph with the vision in the middle and the goals are on the outside, and the way that we achieve those goals. And a lot of these things are actually repeated. So you can see structural insulated panels. Here was a goal for easy to operate technology, and it was also an advanced, where is it there? It was also an advanced construction thing, and it also satisfied our goal of environmental integrity and indoor air quality. And sustainable construction features included consideration for ecology and integrity. So it's a winter use hut only. And so the goat that you saw, there's also grizzlies that frequent the area. So Parks Canada didn't want us to be using that hut in the summertime, so it's a winter use only. And we expect about 700 visitors a year. So it's not going to be used a lot. We had gray water treatment, low visual impact, construction waste management, energy efficient building envelope. Heat was primarily from the sun, so 80 to 90%, because it's so well insulated and so airtight. So we can get away with the heat being supplied mostly from the sun. We use propane because it burns cleaner than wood burning. We have a renewable energy system, and human waste is removed from the site entirely, which is what the Alpine Club does generally for their huts. Everything's collected in barrels and removed from the site. Cold climate construction features included well-insulated thermal building envelope, reduced thermal bridging, airtight construction, heat and ventilation, covered front entrance, and an airlock entry. Now, airlock entry is you walk in the outside door, and there's like a little porch area. Closed door behind you, take off your boots, and then you go into the hut. You go into another door. So that little space there is called an airlock entry. Heating is the sun and the propane. And ventilation is provided by fans that remove the moisture, but you know, in a pinch, if that broke down, you could always open a window. And moisture control strategies included heat, ventilation, super insulation, minimal thermal bridging. We kept the furnishings away from the exterior walls. So I've seen in some huts where, you know, the mattress that's provided in the sleeping areas, how that's right up against the exterior wall. And if you lift that away, sometimes there's condensation that happens in there, and mold can develop. So the reason that happens is because that mattress is acting like a insulation, keeping the warm air from inside from that surface of the exterior wall. So this is where the Deplu hut fits. It has about R45 walls, a little bit less than Passive House, which starts at about 50 but kind of goes up from there. So pretty good insulation. Another one of its main features is the SIP panels, the structural insulated panels, which are on the floors, the wall, and the roof. They are structural, insulation, air barrier, and vapor barrier all in one. And the reason we picked them for the most part is for the short assembly time, because it's a remote environment, and weather can set in as it did, and we wanted it to go up fast. They're strong, high insulating value, airtight, reduced thermal bridging, moisture control, and fire resistant. And of course we have a healthy indoor environment. Conclusions: alpine construction can feature sustainable construction and cold climate construction. And cold climate during construction can play a significant role, which it did. And I just wanted to point out some of the resources that I found really useful. Cold Climate Housing Research Center out of Fairbanks, Alaska. Golden. That's a golden website. So if you're interested in cold climate construction, they have a whole lot of research and papers, and you could spend a month in there. ASHRAE, American Society Heating, Refrigerating, and Air Conditioning Engineers, they actually write the code for ventilation. They actually just produced a cold climate building design guide just this year published, so really good resource. Builder's Guide to Cold Climates by Joseph Lisbrick, the Bible, okay? You need one of those. Canadian Centre for Housing Technology was useful, and I also like the CMHC, which is Canada Mortgage and Housing, wood frame house construction, because it also, at the end of each chapter, had some sustainable building features. So thank you very much.